still remember it. Isn't that great? Monty Python was big.
This sort of thing ain't my bag, baby.
Monty Python was big back in the day. Okay, so we're on 0.4, the measurement of distance. I said we're on 0.4, the measurement of distance. No, you get nothing? I thought y'all be like, yeah! Woo! There you go. Look at that eclipse. Here we go. Measurement of distance. Okay, there's a process called triangulation. Have you ever heard of it? No. We're gonna do a lab where you're gonna measure the distance to the top of a tree outside. How are you gonna do that? You're gonna climb up the tree and carry a ruler with you and go all the way to the top of one of those pine trees? Sounds dangerous. Mr. Willis, is there an easier way? Yes. Triangulation.
How about?
Triangulation uses basic geometry to measure distances that are very far away. If you know a baseline and an angle, you can use geometry to figure the distance to the object. Let's get an idea of how to do this. Here are two ladies on one side of a river, and they're trying to find out how far it is to get across the river to this tree. How do you do it? Well, you can figure out the baseline easily enough. You could drop a ruler from one side to the other, or walk, pace it off. It's 100 steps or something like that. Okay? So you can figure out this baseline easily enough. And if you get directly across from the tree, you know that the angle here is going to be 90 degrees. So you simply go over to point B, and you spot the tree, and you use what's the name of the device used to measure angles?
Protractor.
A protractor to measure this angle toward the tree from the baseline. And so if you know this is 90, and let's say that's a 45-degree angle, what do you know that angle is? 45. Y'all have done math before, right? The three angles of a triangle equal 180. So 90 plus 45 plus 45. So if we knew that was 45, we knew that was 45, and we knew this baseline, we can figure out this. Do you know how we can figure it out? We can use, do y'all remember, did y'all do in math? SOHCAHTOA. Do y'all remember that? Famous Indian chief, SOHCAHTOA? No? Do y'all learn about this in math? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So if we were wanting to figure this out, and we knew this, how could we figure it out? Opposite over adjacent, the tangent of this is equal to the opposite over the adjacent. Right? You can figure it out right on the calculator. You see how I'm saying? We're going to actually do this. That's our lab that's coming up soon. Are you afraid? It's the same sort of thing with a tree. Imagine you have a tree outside. Here's the tree. I like drawing trees. Here's the ground. You have paced off a distance from the tree, or I'm actually going to give you a tape measure. So you can measure the distance from a tree. And here's you standing here, smiling. And you know what this is. You know that. Let's say it's 10 meters. And then you're going to sight out this angle, you see. You got to figure out that angle using a protractor. And it's not easy to do, but we'll figure it out. And so if you know this angle, what's this angle right here of this triangle? What's that angle? That's 90. Thank you. And if you figure out that angle with the protractor that sights to the top of the tree, you got it. I got a little device you can use that has a little straw that you look through. And you aim the straw, you look through it, and get it right at the top of the tree. And then the straw is at whatever angle you see. You see what I'm saying? Are you happy with that, Olivia? Triangulation. So how do we use that in astronomy? Can you imagine? Think of a way. You guys are smart. How can we use that in astronomy? Let's say we wanted to find the distance to the moon. Yes, what were you going to say? Let's do the moon. The moon's closer than the stars. The stars are a little bit more difficult to figure out. How could you use this idea?
You can measure 2 points on the Earth and then measure that.
Oh, very nice. Very nice. Okay. What we have to do is we have to understand the idea of parallax. The shift in position of an object against its background. We call that parallax. And I'm going to demonstrate parallax to you right now. I'm going to stand in front of this, and I want everybody to look at me. Y'all looking at me?
Yes.
Okay? I'm standing in front of this, and I'm going to move up forward a little bit. Okay? And I want you to look at me, and I want you to write down in your notebook what letters on the board are kind of behind my head from where you're sitting right now. From where you're sitting right now, what letters on the board are kind of behind my head? Just write it down. Or what part of the board is behind my head from where you're sitting? You got it? You write it down? Think of me as the moon and what's on the board as the background stars. My head is the moon. Is that hard for you to guess?
Well, you moved your head a lot from your lines.
I've moved it?
Yes.
Look forward.
I moved forward?
No, look forward.
Oh, sorry. Okay, now I want you to get up and go to somewhere else in the room and take your notebook with you so you can write down what letters are at this new spot, from this new spot. You have to move some distance away. You'll go back to your seat and put that anywhere.
I'll just carry it with me.
I got all my letters right.
You got them right?
Yeah.
There's no right answer or wrong answer.
Yes.
It should be different. Are the letters different?
I mean, my letters that I was supposed to get are right.
I wish to keep myself.
I didn't have you guessing any letters.
I thought we were supposed to write down the letters that were behind your head.
Write down the letters that were behind my head from one point and the letters that were behind my head from a different point.
That's what I'm saying.
Do you see that they're different?
Yeah, I got the ones right from the other.
I didn't care if you guessed it right or not. Do you see that they're different?
Yeah.
Okay, go back to your regular seat. You got a slight difference?
There's Ellie.
Hey.
How
What's up?
different?
Whoa.
Close up.
Excuse me.
Sorry. The whole thing I
I'm gonna
wanted
break
you to
it.
notice is that the letters are different depending on where you move. Here's something interesting. If you were in the front of the classroom, closer to me, the change in letters would have been more than if you were in the back of the classroom.
Say it again.
Isn't that interesting? Did you do your two measurements from the front?
No, I went to the Michael.
You went to the back? Did anyone stay in the front the whole time? Were you in the front the whole time?
Yeah.
Okay, but you're kind of
Yeah,
far
good.
from me. I tell you what, here's another way to represent it. Hold your finger up in front of your face, kind of real close. Okay? Close your right eye and leave your left eye open, and then close your left eye and leave your right eye open. Do you see how the finger jumps positions as you switch between the two? It's like magic. It's a teleporting finger trick. How does it do that? Isn't that cool? It's one of the most fun things to do. Okay? Isn't that interesting? Now do it with my finger. Do you notice how it doesn't jump very far? The finger doesn't jump very far when you're doing it with a finger that's far away. Am I right, or am I making this up?
You're right.
How far did it jump from where you're sitting? Not much. And how far did it jump when you're right in front of it? A whole lot. Should have jumped more. Is that true? Okay. Well, we call this parallax. The closer something is, the more difference there is between two pictures than the farther something is. You see what I'm saying? So, the bigger, this sentence is important, the bigger the baseline, the greater the shift that the object makes. And if you get your baseline long, you'll see more of a shift than if your baseline is short. And all of these different ideas can come together. And this is what Whalen was saying here. If you get a telescope on one side of the Earth, look at the giant telescope. That'd be a real big one. That'd be hard to build. I'm joking now. If anything strikes you as funny, go ahead and laugh. If you look at the moon from this side of the Earth and look at the moon from this side of the Earth, they'll probably see the moon in different positions. Right? They'll see the moon from this side of the Earth, you see the moon in front of these stars. But from this side of the Earth, you see the moon in front of these stars. And so, you can compare the difference there, which we call the parallax, the movement, the difference between the two pictures, and the greater the movement, the closer the object. Just like your finger moved more when it was close to your face than when it was far away. So if you take two pictures and the object has barely moved, you know it's far away. If you take two pictures and the object is moving a lot, you know the object is close. This is how they find the distance to asteroids when they scope them in their telescope. This is one way they can find them, is they can tell if it's close or far.
So where's this point where there's land on both sides of the Earth?
Oh, you can fly a plane and take the scope out of a plane.
Oh,
Or Hawaii is an island right here.
it's cheating.
Or you don't have to get on exact opposite sides. You can get here and here and figure out that distance there and then just have a smaller triangle. Or you can do it another way. You can you can take the picture here with your own telescope, wait for the Earth to rotate, 12 hours later, take it again, then you'll be on the other side.
Yeah, but then how about the thing you're measuring move too?
That would complicate things. That would complicate things if the thing you're measuring moves. Maybe you could figure that out some other way. You're right, that would complicate things. Easier if they're both taken at the exact same time. Good thinking. But we can use these techniques to get distances, to figure out distances to objects. Just like we're doing triangulation to figure out how tall a tree is. So here we go. As seen from A, the moon appears in front of those stars. As seen from B, the moon appears in front of those stars. And you can mathematically calculate how far the thing is away by how far it's moved, if you know how long your baseline is. You got to know how long your baseline. Any way to get a baseline longer than the size of the Earth?
Use a satellite.
Okay, use a satellite. Yeah? You can put a telescope on a satellite, but you know what? Satellite, even the satellites that we launch that are in geosynchronous orbit around the Earth aren't a whole lot farther from the Earth. Any way we can get a much longer?
You just like multiply the distance and then figure out the angle from that?
Yeah, but some objects are so far away you actually need to take the pictures from longer baseline to get any movement at all. You need a much longer baseline. You can imagine the further you move, the further your baseline is, the more different the picture is going to be because you're coming at more of an angle. There's another way to get even a longer baseline. Y'all just aren't thinking of it.
Stars.
What's that?
The stars.
What about the stars?
Like, see how much they move, like, in comparison with the stars.
Well, let's say we're trying to find the distance to a star, and we're seeing how much they move. Stars are so far away, they barely move at all by this method. Maybe won't even move at all by this method. But if you could somehow increase your baseline, you might be able to get them to move a little bit. How do we increase the baseline? That's what I'm asking. It's not spaceships.
Human ingenuity.
Yeah, that's what I'm waiting for from you guys.
It's in the book.
Consider, let me throw this hint in for you. It's not in, you won't find it in your book,
Oh.
right, in this chapter. It's in a different chapter.
Okay.
Consider this. The Earth moves.
So you're saying take it 6 months later?
Layla got it. Yeah. Here's the sun in the middle. Here's the sun. Here's the Earth. Here's some faraway object. You can take a picture of the faraway object. 6 months later, the Earth's on this side. You take another picture from that side. Then you have a baseline that is what we call 2 AUs. An AU is the distance between the sun and the Earth. It's like 80 million miles. It's something just crazy.
Why is it called AU?
Astronomical unit.
Got it.
1 AU is the difference between the sun and the Earth. So this baseline is 2 AUs long if you just wait 6 months. And when you do that, the nearby stars, the stars that are really close, shift a little bit compared to the background stars. Just a little bit. Just a teeny bit. But just that teeny bit, we can use mathematics to figure out how far those stars are away. So now we know the distances to nearby stars by this parallax shift. Isn't that freaking cool?
Again, how do you know it didn't move?
How do we know that the faraway stars didn't move? We don't. But you would know when the Earth gets back to its original point. If you took the picture again and it hasn't moved, if it's in the same spot. Right? And all the stars out there are actually moving, but they're so far away that the movement that they make is negligible. Our sun is moving too, and that's another thing that could complicate it. But the distances are so vast that it doesn't really make a difference. They started figuring this stuff out in the 1600s. Guys like Galileo figured out that this could be done. And they started figuring out distances to stars. Did you know the Earth is round? Look at a globe. Huh? The Earth is round. We have pictures of the Earth. We know it's round. Did you know that there's still people that think the Earth is flat? It's called the Flat Earth Society.
Wait, why though? Like, why would you do
They're
that?
insane.
Is there a flat Earth society?
Yeah, go online and look it up. Flat Earth Society. What?
Where are they from? New York.
They're they're from all over. I mean, look at a globe. Look, now they're not going to look at that. They don't believe that. They think the Earth's flat. Anyway, no, it is round. And do you know when people first figured out it was round?
200 BC.
Yeah, pretty close to that. There was one guy, his name was Eratosthenes. Say that name with me, Eratosthenes. All at the same time, it has to be all at the same time. 1, 2, 3.
Eratosthenes.
It's a great name to say. As a matter of fact, I'm thinking I'll name my first child Eratosthenes Willis. Think he'll get made fun of? No, he won't, because he'll be a badass. Anyway, Eratosthenes, he figured out conclusive evidence that the Earth is round. And it's really cool how he did it. He did it using simple geometry and just common sense. And I have a video that shows how he did it. And the video is narrated by my favorite scientist of all. His name's Carl Sagan. Have you ever heard of Carl Sagan? He wrote a book called Contact, that's fiction, and it was made into a movie that was kind of famous about our first contact with alien civilizations. And the book is really good, and it's one of the first science fiction books I ever read. There he is on the back there. Carl Sagan became rather famous. He did a series of videos called Cosmos that were aired on TV. And this video, this little clip about Eratosthenes, I took from his video lectures, which I bought and watched, but they used to just show on TV. And they were the first real science TV. This is the first real science TV show. There was a National Geographic show before it. You ever heard that music? You ever heard that before? That was from the National Geographic show. And then they came out with Cosmos, and there were only a couple science shows at the time. Now there's a whole science network, a science channel, and all kinds of shows. But he was one of the first ones with the show. And his show was really good and really interesting. And he wrote all kinds of books. I've got all his books here. He's my favorite author. He was a teacher and a scientist at the same time. He was really good at explaining it. And people used to make fun of his voice because he's got a distinctive voice. There were a lot of impersonators that did his voice. I'll be talking a lot about Carl Sagan during this class because he's just my favorite. But here's a little video about Carl Sagan figuring out that the Earth was round. Not only figuring out that it was round, but figuring out how big it was. And I have to forward it to the right spot. This is the whole video.
Hello, my name is Andrea. When Carl Sagan, Stephen Soder, and I were
That's Carl Sagan's wife. Carl Sagan is dead now. He died of cancer. Died of cancer about 15 years ago.
There was once a time when our little planet seemed immense, when it was the only world we could explore. Its true size was first worked out in a simple and ingenious way by a man who lived here in Egypt in the 3rd century BC. This tower may have been a communications tower, part of a network running along the North African coast by which signal bonfires were used to communicate messages of state. It also may have been used as a lighthouse, a navigational beacon for sailing ships out there in the Mediterranean Sea. It is about 50 kilometers west of what was once one of the great cities of the world, Alexandria. In Alexandria, at that time, there lived a man named Eratosthenes. One of his envious contemporaries called him Beta, the second letter of the Greek alphabet, because he said Eratosthenes was second best in the world in everything. But it seems clear that in many fields, Eratosthenes was alpha. He was an astronomer, historian, geographer, philosopher, poet, theater critic, and mathematician. He was also the chief librarian of the great library of Alexandria. And one day, while reading a papyrus book in the library, he came upon a curious account.
South, he read, at the frontier outpost of Syene, something notable could be seen on the longest day of the year. On June 21st, the shadows of a temple column or a vertical stick would grow shorter as noon approached. And as the hours crept towards midday, the sun's rays would slither down the sides of a deep well, which on other days would remain in shadow. And then, precisely at noon, columns would cast no shadows, and the sun would shine directly down into the water of the well. At that moment, the sun was exactly overhead.
It was an observation that someone else might easily have ignored. Sticks, shadows, reflections in wells, the position of the sun, simple everyday matters of what possible importance might they be. But Eratosthenes was a scientist, and his contemplation of these homely matters changed the world, in a way, made the world. Because Eratosthenes had the presence of mind to experiment, to actually ask whether, back here, near Alexandria, a stick cast a shadow near noon on June the 21st. And it turns out, sticks do. An overly skeptical person might have said that the report from Syene was in error, but it's an absolutely straightforward observation. Why would anyone lie on such a trivial matter?
So let me explain this in case you're not following, or if you're doing something else besides watching. He's a librarian, and he's reading a book that says on June 21st in this town called Syene, which is south of where he is, at noon, when the sun is at its highest point, there's no shadows. The sun's right overhead, so nothing casts a shadow. So he waits a year until the next June 21st, and he remembers this, and he waits till noon on June 21st, and he looks down the well, and he looks at the stick, and it does cast a shadow where he is. That's where we are right now, okay? Now, the normal person might think that the guy in Syene is lying. But Eratosthenes is quite intelligent, as you'll see.
Eratosthenes asked himself how it could be that at the same moment, a stick in Syene would cast no shadow, and a stick in Alexandria, 800 kilometers to the north, would cast a very definite shadow. Here's a map of ancient Egypt. I've inserted two sticks, or obelisks, one up here in Alexandria, and one down here in Syene. Now, if at a certain moment each stick casts no shadow at all, that's perfectly easy to understand, provided the Earth is flat. If the shadow at Syene is at a certain length, and the shadow at Alexandria is the same length, that also makes sense on a flat Earth. But how could it be, Eratosthenes asked, that at the same instant there was no shadow at Syene and a very substantial shadow at Alexandria? The only answer was that the surface of the Earth is curved.
Not only that, but the greater the curvature, the bigger the difference in the lengths of the shadows. The sun is so far away that its rays are parallel when they reach the Earth. Sticks at different angles to the sun's rays will cast shadows at different lengths. For the observed difference in the shadow lengths, the distance between Alexandria and Syene had to be about 7 degrees along the surface of the Earth. By that I mean, if you imagine these sticks extending all the way down to the center of the Earth, they would there intersect at an angle of about 7 degrees. Well, 7 degrees is something like a 50th of the full circumference of the Earth, 360 degrees. Eratosthenes knew the distance between Alexandria and Syene. He knew it was 800 kilometers. Why? Because he hired a man to pace out the entire distance so that he could perform the calculation I'm talking about. Now, 800 kilometers times 50 is 40,000 kilometers. So that must be the circumference of the Earth. That's how far it is to go once around the Earth. That's the right answer. Eratosthenes' only tools were sticks, eyes, feet, and brains, plus a zest for experiment. With those tools, he correctly deduced the circumference of the Earth to high precision, with an error of only a few percent. That's pretty good figuring for 2,200 years ago.
How cool is that? Huh? How about he hired a guy to pace off the distance between the two towns because no one knew exactly how far it was? What if that was your job? 800 kilometers. That's about, what, how many miles? 500 miles.
How do you know he was traveling in a straight line?
I don't know, probably didn't. I don't know, there's a road, I guess.
Oh, no, wrong answer.
That's probably where you get the 3% error. But that's very interesting. And so, when Columbus comes across the ocean to America in 1492, most of the people think he's going to fall off the edge of the earth. Because most of the people think the earth is flat, even at that time, 1,500 years later. Columbus was not at all afraid of this, because he knew about the calculations that had been made way long time before. The learned people on earth knew about this stuff. People that could read, people that went to school, people who were educated knew the earth was round. They knew it not just from this, they knew it for a lot of other ways. You know, another way to easily tell that the earth is round is something we already studied in this class.
Horizon line?
What's that?
Horizon line?
Horizon light?
Line. Like if the earth was
Oh, well,
flat,
that's a different way that I wasn't thinking of. But yeah, there's a horizon line you can't see on forever. And the reason that there is a horizon line is because the earth is round. Is that what you're going to say? If you see a ship coming up over the horizon, you know what part of the ship you see first? Like a sailing vessel, you know what you would see?
top.
The mast, the top, yeah. And you would see it coming up because it's coming up over a curved surface. That's another way to know that the earth is round. There's another way, though. Another way. Back this up. Any way from these pictures that you could tell that the earth might be round?
The shadow of
You know what this is? What's this a picture of? Whoops. Whoa! What happened?
We fell off the edge of the
This sort of thing.
How did it do that? Very. I'm getting some very strange things here. Magic. There's writings from ancient China that talk about this way of telling that the earth is round. Here we go. This is a lunar eclipse where the shadow of the earth comes between the sun and the moon. Here's the moon over here, and the shadow of the earth falls on the moon.
The shadow of the cast is right.
the shadow that the Earth casts is round. This is very upsetting. What happened? What happened to my eclipses? Maybe the battery's getting bad on this. It's acting up. Okay. If you take a close look at this shadow, you can tell that it's a round shadow. And that was noticed by ancients a long time ago. And a few of them, most of them don't know what's happening. Some god is covering up the moon because he's upset about something. But a few said, maybe the Earth's shadow is going over the moon, and you can see that the Earth's shadow is round, so maybe the Earth is round. And they wrote that down, and that's in ancient writings from several thousand years ago, Egyptian and Chinese. And it wasn't really recognized. Again, back in the old days, people are worrying about just getting enough food and things. 5,000 years ago, you're worried about protecting your family and reproducing, and people only live to 30 years old, and you're not really too worried about trying to figure out the secrets of the Earth. But as soon as society evolved and you had people growing food for you, and you had a military protecting you, and you were rich enough, then you could start thinking about the different secrets of the Earth. And so we see once big societies start forming, we see some ideas, some thinking going on, and things like this coming out, which is very interesting. So Eratosthenes wasn't even the first one to suggest that the Earth was round. That had been suggested, but Eratosthenes was able to prove it and measure it, which wasn't able to be done before then. Isn't that a great story?
Sorry.
So yeah, so there are, so there are still people that think the Earth is flat, and you're always going to have people that have kind of weird beliefs and such, and you just leave them alone. You don't want to get too close to them; they might hurt you. Page 18, section 0.5 talks about the scientific method, and oh, by the way, on page 19. You need to put a little star by sizing up the planet Earth. Just because that's a little blue discovery section, that doesn't mean to just skip it. Often we can just skip those little discovery sections, but that will be included on the test. Okay? And so this last section about science and the scientific method, I'm kind of assuming that you know that. Okay? I'm kind of assuming that you know about the scientific method. Purpose, hypothesis, procedure, results, conclusions. Have y'all had this in other science classes before?
Yes.
So don't really worry about 0.5. I'm not gonna test you on that. Okay, you don't have to read that. Okay. So you read 0.4 tonight, and that's it. Are we good?
When is our first test?
Peace out!